Swayam Prabha. Digital India. Educated India.
Until yesterday, we were talking about the formulation of finite element equations for solid mechanics. And we did extensively for two-dimensional solid mechanics, that is plates or long body, so under plane stress or plane strain condition. And we derived all the equations. There's still a few issues which you'll be able to appreciate when we do a problem. So let's do a numerical example today, and this is regarding a 2D plate. A numerical example. Wherein we take a plate here. And this is 2 meters by 3 meters by 4 meters. So this is the problem where we have a plate here of size 3 meters by 4 meters. And it's acted upon by a force here of 500 newtons per meter. For simplicity, we are assuming it has a thickness of 1 unit. It can even be smaller. It can even be some finite thickness T, but it doesn't make much difference even if you take it to be a unit thickness. So this is, we take it to be under plane stress. So this plane stress assumption will come only while describing the stress-strain relationship, which is the D matrix. And here you might be wondering, T is so thick, so how can it be plane stress? No, it doesn't really matter much. Okay, so what we have here, we discretize it. describes this plate into two elements, triangle and four nodes. Okay, so these are the four nodes and the two elements. And then we can also see the boundary conditions are here. There's a pin connection here. So the boundary conditions here, we can write it in terms of, so if U and V are the displacements in x and y directions, so we can say that U1 and V1 are 0 here, and here then node number 4 is on a sliding support where it can freely slide in the y direction, and only its constraint is only in the x direction. So that means that U4 is 0. Okay, so this is as far as the problem is concerned. Now let's look at the development of various elemental equations. So we go element by element. So what essentially we have to derive is K times U is equal to F. So K is the stiffness matrix, U is the vector of displacement, and F is the force, nodal forces. So now let's look at element by element. Element 1, where I is 1, K is 2, and K is, so this is the three nodes, and x, y coordinates are 0, 0, and 3, 0, and 3, 4. And here Bi is I'm just writing 1 here. 2A is minus 0.33. Bj is yk minus yi. Plus 0.33, and pk is 0. So similarly we have Ci, which is xk minus xj by Ca 0. So we have all this formula. Okay, so these are Bi, Bj, Bk, and area is of course, of course I use the area here, but by any chance, if the element is odd, okay, so that's just for the sake of completeness, I wrote it. So what is the B matrix, which is important here? So the B matrix here, I'll just write it for 1. It is BI0, BJ0, and so B is the relationship between strain and the displacements, nodal displacements, Ci, Bi. So this is the general formula, and you can write it as minus 0.33, 0.33, 0, 0, 0, 0. There's one more 0 here. Minus 0.25, 0, 0.25. Ci, Bi, and Cj, Bj, 0.250. Okay, so this is the B matrix. And then what else we require is the D is nothing but E by 1 minus mu square. This is for plane stress. So substituting these values, so we get 10 to the power of 11, 2.24, okay, so this is the D matrix, B and D. And now we know the K of element 1 is given by P transpose D So this is the general formula where B is the matrix that is given there and D is the material relationship, and again B here. And then this A is the area of the element and T is the thickness. If you want, you can put it. Otherwise, it can even be 1. Okay. So substituting all these things, so the size of this will be, so B transpose will be 6 by 3. This is 3 by 3 and 3 by 6. And totally this will be a 6 by 6. Okay. So we can substitute all these things. You can do it with your calculator, or you can use a little bit of programming, MATLAB, and then you can evaluate this. So I'll give this here. So it's 1.49. Just for the sake of completeness, I'm writing 0.280 minus 0.28. So I'll just write only the upper triangular matrix. This is symmetric. 0.42 minus 0.56 minus 0.420, 1.80 minus 0.7 minus 0.315 to 8, 1.4, 0.42 minus 0.84, 0.315, 0. Okay, so this is the K matrix, right? And so similarly, we can also do it for element 2. Element number 2, I think I'll leave it as an exercise here. So here the IJK are 1, 3, 4. These are the node numbers. And then you go through the same procedure. You write down the XY coordinates of 1, 3, 4 and calculate BI, BJ, BK and put it in this B, and D is the same. So go through B transpose DB. So if you do that, so the K for the element 2 will look like this. I'll write it all the same just so that you can verify it yourself. Minus 0.42, minus 0.315, 0.84, 0.28, 0.28 minus 0.84, 0, 0.28, 0.86, sorry, this is 0.56, 0.42 minus 0.56, 1.8, minus 0.7 here. Okay, so this is as far as the two stiffness matrix are concerned. And what else? So of course these have to be assembled. We'll just do that. But simultaneously, as you calculate the stiffness matrices of the two elements, you also have to find out the nodal load vector. So what is the nodal load vector here? So that is because of the traction on the vertical face here. So the nodal load, will just assemble that, and let's just assemble this nodal load. Nodal load vector here, and for the element 1, so this is IJK. So this is very easy. So this is 1, 2, 3 here, and which will consist of, okay, so what it will consist of? So there is a force here. There is the distributed traction here. There is no other force. There is no body force here. So on 1, 2, for example, so what will be here? This is, as far as this side is concerned, there is no load here. The two components, F1x, for example, Fyx, Fyy, Fky, Fkx. So this, as far as this is concerned, So this is Ni times on this face it is 0. So all these two components are 0 here. And then this fjx here, that is number 2. So that is fj. So if you recall, so this is nothing but your sjk by 2 times tx. I'll just write it here, sjk by 2 ty, right? So this is tx ty on jk, and sjk by 2 tx and sjk by 2 ty, right? So this is how the side jk, that is number 2, 3, is being acted upon by the nodal forces because of the traction here. So it is nothing but 0, 0, and the side length here is 4. 4 multiplied by this 500, it's 2000. So it is actually, so it is 1000, 0, half of it, and 0. Okay, so this is what the nodal loads are, and this is for element 1, and for element 2 there is no other traction, so this is all zeros. Okay, so this is what it is. Now let's try to assemble these elemental matrices into the global stiffness matrices, global stiffness and the load vector. So the global will consist of, this is K global. If you want, you can put K global. So we have we have 4 nodes and 8 degrees of freedom. So these 8 degrees of freedom correspond to what? So it is U1, V1. They correspond to this, U3, V3, and U4, V4. Just to locate it, the same thing you can write it, U1. Okay, so these are the 4 nodes and 8 degrees of freedom total. And then this K1 has to go there. So where will it go there? So here it is IJK or 1, 2, 3. So it is U1, V1, U2. So these are very clearly just the first 3 nodes. So that means that this will go here. Okay, so where will it go? So that means that the first thing will go here. So this top 6 by 6 will go here. So that means that it is something like, yeah, so this will go here. For example, you can start putting it here, 1.49 and so on all the way up to here, 0.884, like. So this is a very simple element. Apart from this, now you can fill it up and then, okay. Now coming to the second element, so it is 1, 3, 4, where you have U1, V1, U3, V3, U4, V4. So what is this will go to? So these things will go to where? So it will go to U1, V1, and only 2 is not there. So I'll just mark it here. So these things correspond to U1 V1, U3 V3, U4 V4. So that's what I marked in yellow. Right? Okay. So those things, for example, this will go to here plus 0.315. So totally it becomes 1.803. Okay. So like this, so you have to assemble everything and then it will become, this is 1.803. Okay. 0 minus 1.49, 0.28, 0 minus 0.7, 0.315 and 0.42. Okay, so like this, so you can fill up the whole thing. In fact, on this element 1, element 2 will go into these places, so they have to be added. And then this multiplied with U1, anyway, I wrote it here. So the equation is, so I'll remove this here. So the equation is this K multiplied by the displacements here will become the nodal forces. So what is this nodal forces here? So that is element 1. So it is 0, 0, 1000, 0, 1000, and the other things are 0. Okay, so these are nodal forces. So this is the equation which we have here, and then so assume that all these things are filled up. Okay, so it just becomes 8 by 8 matrix, and then on the right side you have this force vector, and then you have to solve for this one. So there are a couple of issues here. Is that it looks like that you have to take an inversion and you can solve it. That's what appears to be as a mathematical approach. So if you think that this is assembled equation, assembled thing, so this involves K times U is equal to F. So it looks like U is K inverse So what is the catch here? So you should be able to invert K and get K inverse. But if you feed this into your MATLAB or something like that, the K inverse doesn't exist because this K, the determinant is 0. In fact, if you look at the rank, this is what we were discussing earlier in the beginning. So what is the rank of this matrix? So the rank of this matrix is only, this being 8 by 8, so this is only 5. So that means that there are 5 independent equations here, or on the other hand, they can say there are 5 independent equations, or we say that there are 8 minus 5, that is the rigid body modes. What are the rigid body modes here? So this is a 2D plate, and so the rigid body modes are, the plate can move in the x direction, the plate can move in the y direction, the plate can rotate about a z axis. So that way, so for those kind of modes which we call as rigid body, so there need not be any force application. Without any force application, the body can undergo rigid body. So that means that under the action of these forces, so unless we restrain these rigid body modes, so we will not be able to get a non-zero solution. So here, obviously the rigid body modes have been removed here, U1, V1 0, U4 is 0. So we have minimum. So U1, V1 and U4 are 0. So these restrict, these remove rigid body. Okay, and we'll continue this one in our next lecture. We'll spend some time and then we'll move on to some other topic. So for the moment, we'll stop.